Okay, today we are going to talk about shafts, okay? And then we will extend to shaft components. Okay, now what is a shaft? Uh, Shaft is actually a circular rotating member that transmit power. Okay? So basically, shaft is used for power transmission, and it rotates, so there is motion in there, and it is generally of a circular cross section. That means that uh, this will be a shaft. Uh, this is how it will somewhat look like. Okay, and it rotates. Okay. Uh, so uh, for shaft, it is also when we say shaft components, it is also used to provide the excess of rotation or oscillation for elements such as you know uh, gears, pulleys, flywheels, cranks, sprockets, etc. So basically, we mount different, various components on shafts, जैसे गियर्स, ऊपर ऊपर जो जिक्र किया गया है, पुलिस, cranks, cranks, etc. Right now, um, and for shafts, what do we need to do when we design a shaft? Let me just um, see, because this is going to be a shaft, right? Just a plain simple shaft is going to look like this. So it will have some diameter. The shaft will have some diameter d, and it will have length, some length L, for example. So if I want to design this shaft, what am I looking at? Basically, in a shaft, the first thing that I'll be looking at is what material should I use for this shaft. Okay, so I should determine the material when I'm designing a shaft. The second thing would be what should be the diameter of this shaft. Okay, and generally the length of the shaft is according to the space that is available, and the function that you take from it. So length, that is easy. You can just say, you want a shaft of this length. But these two are the main, factors, that first you will choose a material and then you will look for a certain diameter of a shaft. Now, we took this shaft because we wanted it to be very simple. But it is not very simple to find out, though it is easy to find out the diameter of a shaft once you choose a material, but it is a very lengthy or cumbersome process. So, simple shafts, they might not, this shaft might not be a very good representative at all the times, because shafts might look like this. When you put them in actual application, uh, this is what they will look like, that they will not have a uniform cross section. The cross section might change. Okay, so we might have a shaft like this, um, and then you know you will want to find out, what are the diameters of this shaft, d1, d2, d3, d4, and so on. Okay. um, as far as the material is concerned, the shaft material, it is generally steel. So steels are used. For example, SAE 1020 to 1050 steels without heat treatment. Um, you can have heat treated shafts, SAE 1040, 4140, 50. So these standards of steels are used as shafts, shaft materials. Sometimes it is required that we harden the surface of this shaft. Um, Not all the time, but if you need to harden the surface, you again can do that and use these SAE 1020, 8620, so on. Now, as far as the shaft is concerned, the layout of a shaft is concerned, um, since uh, it's regarding the length of the shaft and the components that are mounted on the shaft. So there are certain things that you should do and you should not do when we are talking about shaft layout. First of all, use shoulders for axial location. Okay, when you put a shaft in an application, this shaft is going to be supported, right? And that support comes from either bearings or shoulders, right? So first of all, when you want to look, for this location of the shaft, at this position you need to support the shaft from here, and you also need to support the shaft in this direction so that it doesn't go axially. So for that purpose, you can put a shoulder in a shaft, and the shoulder would look like this, right? And you put this in a groove, and the shaft will not, you know, move or dislocate in this direction. So that is one thing, that you will use shoulders. The length of the cantilever should be kept short to minimize the deflection, which is made for ease of mounting. Okay. There will be situations. First of all, you should keep the length of a shaft as short as possible. Length should be minimum, right? Why would you want to use a long span shaft in which you will see you will have deflections and other problems of support, you should use a minimum length of a shaft anyways. But sometimes um, you use a shaft where the support of the shaft is, you know, for example, here you have a bearing and then you have a bearing over here. And then some portion of the shaft is cantilevered. For example, this portion is cantilevered. ठीक है जी? So in that case, you should keep this cantilever as short as possible because you might use this for, mounting a pulley or a gear or something like that. Okay, so try to keep this cantilever also as minimum as possible. So that is what we are saying, that keep this minimum so that we don't have a lot of deflection over here in the shaft. Um, use two support bearings for a shaft. Keep the length as short as possible. Okay, so that is what we already said. Use shoulders, retaining rings. We have retaining rings, pins to transmit axial load into the shaft. Now, as we said over here, instead of a shoulder, you can use pins. You can use. You're familiar with pins. Pin is just a circular, you know, uh, rod like this, a short rod like this. You can use that for retaining the position of the shaft. Um, and there are retaining rings that you mount on the shaft over here and put that in a group, or put that in such a way that the shaft does not move in that direction. Okay? Now, also, you should use one bearing that carry the axial load. Okay? This is the shaft will have um, loads that you are supporting over here, but in this direction or in along the axis of the shaft, or thrust loads might be there. So what you should do is you should use one axial bearing. And if you remember, when we discussed bearings, this is what we said, that one bearing should take the axial or the thrust load, and that thrust load um, was taken out at one of the bearings. And in the problems that we did, we also specified that bearing A is taking the load or bearing B is taking the load. Generally, we mark it as bearing A, the bearing that takes the axial load. Now, there are torque transfer elements that you use when you mount other uh, components on shafts. For example, keys. So key, you would have seen key that in a shaft, you know uh, there is a keyway, and then you put a key over here to secure any pulley or a gear in here. So this key is used uh, for torque transfer. Eh, the pulley, when the shaft rotates, this pulley is going to, or this gear is going to rotate too, because of this uh, key. Okay, you can put keys in different configurations. You can put multiple keys in there. But I'm sure that you would have seen a key before or read about it before. Now, splines, splines are made on shafts. For example, it will mimic a permanent key on a shaft. For example, if you look at a shaft, it will a splined shaft would look like this. If you remember in clutches, when we discussed clutches, there was a clutch, the axial clutch plate, and in the clutch plate, there is a splined shaft that goes in there. But anyways, a, a, a splined shaft would look somewhat like this. ठीक है. So this is round, but it has these key these splines in there, and these splines would go, you know, in into the whatever you mount on it, that would go around these splines, so they act like as if they these like permanent keys in the shaft. So you have already, you know, you have these are pre-manufactured. These splines are pre-manufactured in a shaft. Okay. You have set screws. If you look at the hub of a pulley, or there is a screw that you would put instead of, you know, um, and that is known as a set screw. That would go into this pulley and then into the shaft a little bit. You can have press fit, like shrink fit on a shaft. So you just put a component in there which has a smaller diameter than the shaft, and you force fit that into the shaft so that it does not move. There is no slip in there. Okay. So these are the transmission, you know, these are um, some torque transfer elements that we would use. Um, Again, when you are considering a shaft, consideration should be given to the method of assembling the components onto the shaft and the shaft assembly into the frame. And also, when you put components on a shaft, you should also consider disassembly, okay? Because that is also a problem. If you have to fix something, you do not have to open the shaft fully. Similarly, if you have to put gears like helical gears, you should minimize the thrust load. And how would you do that? You would put them in opposite direction. So put them in opposite direction to each other so that the thrust goes off. So these are some, you know, uh, some guidelines for setting up the layout of a shaft. ठीक है जी? Now, these are some examples on how, you know, um, the shaft is using tapered roller bearings over here. That is taking the thrust load. ठीक है जी? Similarly, if you look over here, arrangement showing bearings and inner ring press fitted. So the inner rings are press fitted over here. These are different arrangements that we talked about right now. Okay, so have a look at these. Now, when we design a shaft, the first thing that we should look at is the stresses in the shaft. Okay? So we should determine these stresses rightly, and then we should design the shaft in such a way that these stresses are mm, being, you know, um, these stresses are not that much that it will fail the shaft. Now, first of all, let's see. Um, Shafts, there are fluctuating stresses, means that sometimes they go up, sometimes they go down. So this means that there are loads that are cyclic in nature. So, and if we look at a shaft, the two main stresses or the dominant stresses that we have in shafts, those are, what do you think those are? Like, for example, this is a shaft. What do you think the stresses are in here? Okay, this shaft is rotating, right? So first of all, this shaft, if you have a support, bending stress is the important one. ठीक है जी? तो the dominant stress in here is, the first one is bending stress. Okay. Now, also, since this shaft is rotating, therefore, we are expecting that there will be torsional stress. Okay. Now, when we have cyclic loads, we know that we have two kinds of forces that we talk about. One is the mid-range force, or and the other one is the alternating force. So the alternating force is represented by Fa, and that is equal to the F max plus, sorry, minus, it's not plus, minus F min, because the force fluctuates between these two, divided by 2. And then the component which is called the mid-range force, that is equal to F max plus F min, the average or the mean of these two forces divided by 2. Okay? And the stress associated with the alternating force is known as the alternating stress, and associated the with the mid-range force, that is known as the mid-range stress. So let's see. For bending, we know that bending stress is equal to, I'll just write it over here. Bending stress is equal to MC over I. Okay. So we know that bending stress is equal to MC over I. Similarly, torsional stress is equal to TC by J. Okay. So now I have two components of bending and two components of torsion. So the alternating force, or the alternating force, is causing a, the alternating force is causing an alternating uh, sorry, the alternating force is causing an alternating bending stress and an alternating mid-range stress. So first of all, my I'm talking about sigma A, which is the alternating bending stress. So that will be equal to MC over I, but M will be MA. Okay? So I'll just use the moment which is due to the alternating component. And similarly, I'll have a mid-range bending, which is MM C over I. But there is also going to be, this is not the very correct stress, because there is going to be some stress concentration in there, and therefore we are going to use a stress concentration factor Kf over here. ठीक है जी. So therefore देखिए, अगर आप, if you look at these two equations which I wrote above, these are the two equations that represent the bending stress in a shaft, which is the alternating stress and the mid-range stress. Similarly, I'll have torsional stress, which is Tc by J, but there is going to be a stress concentration factor Kfs there. Okay? Now, let's customize, or let's write equations of stresses for a shaft. Let's consider that we have a solid shaft, a solid round shaft. So this is going to be the cross-sectional area of the shaft. and let's say that the diameter of this is d, small d. Okay. Now, can I write the area for this shaft? That is going to be pi by 4 d square. Similarly, can I write j for this? J, what will be j equal to? Pi by 32 d4 इसके बराबर होगा, right? So we know these quantities, and what will be c? C equal to, c will be equal to, देखें, for example, let's take the stress over here. uh, what will be c in these equations? Since it is a shaft, so these stresses are going to be maximum at the radius. Okay? So that will be, the radius will be d by 2. If the diameter of the shaft is d, then our c is going to be d by 2, because we are talking about the maximum stresses of in the shaft. So c जो है, that will become d by 2. Now, similarly, we can, have I circular shaft ke liye. And now putting all these values in the above equations, 7-1 and 7-2, this is what we are going to get. K sigma A will be equal to Kf 32 Ma over pi d cube. We just put the values of I and C in there. Okay? Similarly, sigma m will be equal to Kf 32 over pi d cube. Tau A will be equal to 16 Ta over pi d cube, and tau m will be equal to Kf as 16 Tm over pi d cube, where this T is the torque, the transmitted torque, yeah, the torque in the shaft. Okay? MM and MA are the mid-range and alternating bending moments. TM and TA are the mid-range and alternating torques. And KF and KFS are the fatigue stress concentration factors for bending and torsion. So these are now the equations for sigma A, tau A, sigma M, and tau M. Now we can combine these stresses using the distortion failure theory, the von Mises stresses for rotating shaft. We can go ahead and find that. And we know that sigma A dash from your solid mechanics, that will be equal to sigma A square plus 3 times tau A square under the root. Okay? And similarly, sigma M will be equal to sigma M square plus 3 times tau m square under the root. So just take those values from these equations and put them over here, right? So plugging in those values, this is what we are going to get, that our sigma A dash and sigma M dash, these are the von Mises stresses. Now, so we got these two equations here. Now, note that stress concentration factors are sometimes considered optional for mid-range components with ductile material. If the material is ductile, then you will take some of the stress concentration factors will go away because of the capacity of the ductile material to yield locally and at discontinuities. So you would not need that. Anyways, if you look at this figure, this gives you the different criterias that we use. Okay, this is the mid-range stress and the alternating stress. Okay, and these are different criterias, that failure criterias that we use. If you remember the failure theories, तो आपने failure theories में पढ़ा था, and now these are the different criteria. For example, Gerber criteria, there is a ASME elliptic criteria, modified Goodman uh, theory. Well, we use the modified Goodman line and the Soderberg line. So all these are yield this is the yield line. So you should also consider this, because some of these are outside this line, so they are not considering yielding over here. Anyways, what we mean here is that these equivalent and alternating mid-range stresses can be evaluated using the appropriate failure theory. Okay, so any of these failure theories can be used. For example, the modified Goodman or D-elliptic, or whichever you want to use. Let's just take one example right now. Okay, if you are using the modified Goodman theory, so the modified Goodman theory says, okay, what do we want to do over here? We are going to design a shaft. Okay, so I'm going to take this space, design a shaft. Okay, now what are you going to look at when you are designing a shaft? Okay, you will have a material that you have selected, and that material will have some strengths. Those strengths will be your SY, which is the yield strength, your SUT, which is the ultimate strength, and your SE, which is the endurance strength. Okay? Now, you will be judging, or you will be taking these strengths and looking at the stresses in the shaft. Now, what are those stresses in the shaft? Those stresses in the shaft are sigma A dash, जिसकी अभी हमने बात की, and sigma M dash. So you are going to look at these, and then you are going to come up with the dimensions of the shaft, and the dimensions of the shaft are basically the diameters of the shaft at different sections. So if it's just a plain shaft with one cross section area, then it's just one diameter that you would find. So the different criterias, there are different equations for these different criterias, and you can use any of these criterias, but looking at it, okay, why are you using that criteria? Anyways, for example, the Goodman criteria says, the modified Goodman criteria, which is modified for shaft, it says that if just uh, look at these that I just put in over here. The strengths and the stresses. Um, it says that sigma A dash divided by the endurance limit, the endurance strength, plus sigma M dash divided by SUT. This should be equal to 1 over N. This is your modified Goodman theory. Now, what is N? This is the factor of safety. Now, what is this? This is the alternating one means stress. One means stress, the mid-range one means stress. And what are these? The strengths of the material. So basically, this is what we are doing, that we are comparing these. And then you can calculate your factor of safety. Right? Now, over here, if you look over here, which is this equation, we already have calculated sigma A dash, and we already have calculated sigma M dash, and your SE and SUT will come from the material. So you can go ahead and find your N, factor of safety, if you know the diameter, because in these stresses there is going to be the term diameter somewhere. So if you know all these values, you know the stresses, or you can find your diameter from here, diameter of the shaft. Okay? For example, now your sigma A, what is your sigma A equal to? You already know, okay, it is equal to this value, and sigma A dash, and your sigma M dash is equal to this value. So take these values and put them in this equation. ठीक है जी. So if you take those values for sigma a dash, so go ahead and put that, which is 416 और pi d cube हमने अगर common ले लिया है दोनों से, because we are putting the values of sigma a dash and sigma m dash, so they have some things in common. We took those out. तो देखिए 1 over SE आपके पास रह जाएगा, and then this and 1 over SUT and then this. ठीक है जी. ये बेसिकली दिस इक्वेशन में, इस इक्वेशन में हमने क्या डाला है, सिग्मा ए डैश की वैल्यू एंड सिग्मा एम डैश की वैल्यू. ठीक है जी. देन यू गेट दिस इक्वेशन. सो नाउ एज आई सेड कि आपके पास यहाँ पे देखें देयर इज अ डी क्यूब टर्म. what is this d cube? This is basically the diameter of the shaft, of the shaft that you are going to calculate. So put that on one side and remove the rest of the other, you know, parameters to the to the other side. So on the left hand side you have d, and you move the rest of them over here. So now you can calculate your value of d, and that will be the diameter of the shaft using modified Goodman criteria. ठीक है जी. Any question? Any question?
No, sir.